All right, so our last exercise is about using other bases other than a base of E to be able to then differentiate things. Okay, so there is a reminder at the top of the page that we have our change of base formula, which we will need to use. So there is an example here. If we have log base 7 of x, we want to change to base E because differentiating our rules are always in base E. So we change it to log base E of the x over log base E of the 7. Now, the next little step here, we just, the log E of 7, you bring that out the front, so 1 over log base E of 7, because that part there is just a number. It's messy, it's a bit awkward, but that is just a number. So when I differentiate it, it's just going to be sitting in the front. And I can then differentiate the log base E of x, which we know how to do. Okay, so let's have a look. There's a few other types of questions in here as well. So question number 1, grab one of those on the way in, please, boys. Express the function log base 5 of x in terms of the function log base E of x. So this is practicing using our change of base. So I want y equals, I want to change it to log base E, and it'll be x on the top and log base E of 5 on the bottom. Okay, so change of base, so it is now in terms of log base E of x. All right, part B. Use the ln, which is log base E, button on your calculator to approximate to 4 decimal places. Now, if you're doing with this the old calculator, this is meant to be, you don't need to because you've got your new calculator, so you can just type it in with a base of 4. But if you were doing it old school, you would do ln of 20 over ln of 4. And either way, it's going to give you the same answer. What do you get to 4 decimal places? 2.1610. Okay, so let's do that again. If I do the change of base, it'll be log base E or ln of 0.05 over log base E of 6, which you should get negative 1.6720. All right, so you don't, because you have your lovely new calculators, you can just type them in from there. But it is good to practice change of base because we are going to need that for the differentiating part that's coming. Part C says, use your answers in part, we want to check our answers in part B by using the power buttons. So either x to the power of y, or we have the x with the little box on the calculator. So what that's wanting, go back to part 1 of B there. Remember that a logarithm, if we were to try and answer this logarithm without our calculators, a logarithm is asking you 4 to the power of what gives 20. And we've just found that the answer is this. So if I want to check it with the power button, I would say that 4 to the power of the 2.1610 should be equal to the 20. Is it? Type it in. 4 to the power of that. It's not going to be perfect, but it should be pretty close. What do you get? It does give you exactly 20, does it? Oh, you just rounded it? Yeah. Okay, so if there's a few extra decimal places in there, that's because this was a rounded answer, remember. So it's not perfect, but it is approximately equal to 20. And we can check the other one. The base is 6, so it should be 6 to the power of negative 1.6720, and that should be approximately equal to the 0.05. Probably a few decimal places out because this was rounded. Okay, does that make sense? All right. Question 2, we finally get to the main event. It says use the change of base formula to differentiate. That's what we want to know. How do I differentiate a log base 2 of x? Okay, so the deal is we have to change the base to a log base e. So that y will be equal to log base e of x over log base e of 2. Now, like you saw in that form at the very top of the page, I want to bring this denominator, I'm going to bring it out the front. It's just a number. There's no x's in here. I'm bringing the number part out the front. So it would be 1 over log base e of 2 times by log base e of x. You can see how that's the same thing? I'm just sliding this as a fraction out the front. Okay? Now remember I said this is a number. So when you differentiate something like 2x, the 2 that is sitting out the front, when you differentiate it, the x disappears, but the 2 is still sitting there, right? So the same thing's going to happen here. When I differentiate this, I'm going to differentiate the x part, but the number part's just going to stay sitting there. Okay? So, leave, well, so this is for y dash, the derivative. The number part stays where it is. And I differentiate log base e of x, which is 1 over x. Okay, and then you can just times the two things together. So it'd be 1 over, now, log e of 2, if I put the x there, that's a problem. Because it looks like it's log of 2x, or the 2x's together. So when you have that kind of thing, move the x out the front, so you know it's an x times by the log base e of 2. Okay, let's try another one. Part B, log base a of x. Okay, I'm just putting an a in there. A would represent some constant, don't know what it is, but it would be a number, not a variable. Okay, so change of base would be log base e of x over log base e of a. Split it to be log base e of a times by log base e of x. Sorry, 1 over the log base e of a, sliding it out the front. Just like last time, when I differentiate y dash equals 1 over log base e of a times by 1 over x. Or in other words, let's just put the x straight in there. Yeah? So this kind of gives us a formula. And if you look over on the next page, this is the formula that is on the reference sheet. If you are differentiating a log with a base of a, the derivative of the function is on the top over the function, but you'll have log base e of whatever a is times by at the front of that denominator. Okay? Which is what we were just seeing when I was doing it with the full working out. Okay, but this might save us a little bit of time. Okay, so let's do these next couple with that formula, see if it's a little tiny bit shorter. If I want to differentiate log base 10 of x, y dash equals, the formula says I want the derivative of the function on the top. My function is an x, so the derivative is 1. So it'll be 1 over log base a. What is a in my question? 10. So I'm going to have log base, it's log base e, or ln, of 10. And then I'm going to multiply that by the function, which is x, but I'm not going to put the x here, I'm going to put it in front. So x ln 10 on the bottom. That was shorter, let's do it again. Y dash equals, does that say 1.2? I think it does. I think it's 1.2. Okay, so using our formula, we want the derivative of the function on the top. The function is again x. So derivative of x is 1 over, formula says log base a, so that means ln, sorry, not log base e, it's log base e of a, say it correctly. So it's ln of 1.2. And The derivative of the function itself, is an x, so I'm multiplying the x on the denominator. We okay with this?
Yep.
Yes? All right, because now we need to kind of do some more application-y kind of things here. Part 4, question 4. Show that the tangent to y equals log base a of x at the x-intercept has a gradient of 1 over log base e of a. So I can't use this. This is the answer that I have to try and get to. All right? So if I'm after a tangent, I need to differentiate it. So let's say y dash equals, what's the derivative of my function? My function is, in here, I'm looking at this, the function is the x. So the derivative is 1 over ln of a, good, times by my function, which is x. So there's my derivative. Next part, I want the tangent, I want to show the tangent at the x-intercept. Doesn't actually tell me what the x-intercept is. It's a log graph. Where is the x-intercept of a log graph? 1. So that's kind of something we need to know. We're going to say the x-intercept is at x equals 1. So that means that y dash equals 1 over x is 1 times ln of a. Okay, so 1 times, I don't really need that, ln is log base e of a. Now the only reason I changed that to log base e is because I want it to look like that, to show that I got back to this thing that I was meant to get to. Yeah? Done. Next one, B. Show that the function y equals log base e of x is the only logarithmic function whose gradient at the x-intercept is exactly 1. Okay, so this is saying that the derivative y dash is equal to 1. Okay, now I'm going to use, this is a part B, which means I'm continuing on from part A up here, right? This is my derivative of a log base a of x. If I try and find where that derivative is equal to 1, for what value of a, maybe that will show me it's a base e. That a, okay? So let's try putting that in. My gradient is 1 equals 1 over log base e of a. All right, I have to solve this. What should I do? Yeah, multiply it over. So we're going to have log base e of a equals 1. Now what should I do? Slide the base. Good. So e to the power of 1 equals a. What does that mean? A is equal to e. And remember that a was the base of this original logarithmic function. So if a is equal to e is the only time where the derivative at x equals 1 is equal to 1. Critical property of our log base e graph. So let's write a little conclusion. Therefore, y equals log base e of x is the only logarithm whose gradient is 1 at the x-intercept. All right, next page. So we have a note at the top of the page. We've seen these before. If we have e to the power of log base e of a, so as long as this is log base e, if the base of the logarithm is the same as the base of the exponential, so e here, e there, then the exponential and the log base e cancel each other out, and it's just equal to a. Now this one is a little bit different. I could rewrite that so that it makes a little bit more sense. I could change that to be e to the power of log base e of a to the power of x. All I'm doing is using one of my log laws to say that x there can go up to the top here to be a power. Because then, here's my e log base e, cancel each other out, and then a to the power of x is equal to a to the power of x. Right? So this is saying if it's in this form, then if you have e to the power of x log e of a, it's going to be equal to a to the power of x. And that's why when you do that little rearrangement. Okay? So question 5. Express these numbers as functions, n functions, as powers of e. Okay? So 3 could be written with a base of e if I use this. Right? So I'm going to make it e to the power of log base e of 3 because the exponential and the logarithm will cancel each other out. So it'll be e to the log base e of 3. Made it way messier, but I have done what it asked. I have written it as a function of and a power of e. So same thing with 7. I could write that as e to the power of log base e of 7. All right, what about the 2 to the x one? That's using the second rule that I wrote there. So what is that going to be equal to? E to the power of x log e of 2. Very good. And one more time. 4 to the minus x is e to the power of minus x, the power is at the front, log base e of 4. Okay, why on earth are we doing that? Well, because we are now wanting to differentiate things that have powers of x but are not a base of e. So we know that the derivative of e to the x is e to the x, but what's the derivative of a to the something x? All right? Now this is the formula that we can use. But I'm not going to do that. I'm going to do it without the formula first and then with the formula, because you can do it without. Okay? So I'll do down here this question. I'm going to do it twice. So let's divide it down here. First time is going to be without the formula. So without formula. Okay. So if I forgot all about that very unusual formula, I would be starting with y equals 2 to the power of x, and I want to differentiate it. Okay, but what I need to do is change it into a base of e, which is what we were just practicing. Yeah? Remember those rules back there? I can change that to be e to the power of x ln of 2. Log base e of 2. Yeah? That we were just practicing? So then if I want to differentiate that, y dash equals, when we differentiate an exponential, we know how to do that. The derivative of the power comes down the front, which will be ln of 2. Then the exponential stays exactly the same. So it'll be e to the x ln of 2. Look at that. Did it. Okay. We differentiated without the formula, but there was more to this question. It says, hence, find the gradient at the y-intercept correct to 3 significant figures. What is, this is the 2 to the power of x. The y-intercept, what is that a really weird way of saying? We want an x value to sub in. What is the x value at the y-intercept? Any graph, it's always 0, right? So it's a really backwards way of saying it, but it's asking us to sub in when x is equal to 0. All right, so y dash equals ln of 2 times e to the, it's 0 times ln of 2, but it doesn't matter if it's 0 times anything, it's just going to be 0 up here. What's e to the power of 0 equal? 1. So that's just equal to ln of 2. That's exact, but we were asked for 3 significant figures. So type that in your calculator. Yeah, 0.693. Very good. Okay, so second time around, we're going to do it with the formula now. So, if I have got something with a to the power of a function, my a is going to be equal to 2, and my function is the x. Right? A is 2, function is x. That makes sense? Alright, so using the formula, it says ln of whatever a is. So that's going to be ln of 2. Then I want to multiply that by the derivative of my function. What was my function? X. So what's my derivative? 1. Then I multiply that by my original a to the power of f of x, which in my case is 2 to the power of x, the original thing that I was trying to differentiate. Okay, so obviously that 1 in the middle there doesn't really do anything. So it's ln times 2 to the x. All right, and then we would sub in, like last time, that x is equal to 0, which we would get y dash equals ln of 2 times 2 to the power of 0. 2 to the power of 0 is still equal to 1, so we're still getting ln of 2. Or 0.693. Okay, so it is a bit shorter, as long as you know how to use that formula. All right, next page, last page, question 7. Show that y equals x plus 1 meets the curve y equals 2 to the x at 0, 1, and 1, 2. Now, normally, when we are given a question where we're trying to find where two curves meet, we want to do simultaneous equations. Small problem. If I do that, I'm going to have 2 to the x equals x plus 1. Yeah. Okay? Can't do that when I have an x in the power and also x is on the other side. Okay? So, what I have to do is just check this by substitution. They have given me the points. I just have to confirm that these are the points. Okay? So, I'm going to check, well, I've drawn down the middle, so I'm going to check one on each side. So, by substitution, because simultaneous equations won't work. By substitution, I'm going to check when x is equal to 0. Okay, that's my first one here. X is equal to 0. I'm going to check it, put it into both equations, and hopefully both of them will go through y is 1. Okay, so if I put it into, let's call this equation 1, and this one equation 2. So if I put it into equation 1, I'm going to get y equals 0 plus 1. Oh, good news, that equals 1. If I put it into equation 2, I get y equals 2 to the power of 0, which also equals 1. All right, so I've just confirmed that both of those graphs are going through or are at the point 0, 1. I subbed 0 into both of them, and I got 1 for both of them. Do the same thing with the second point. So now when x is equal to 1, and I'm hoping that they'll both come out to be at 2. Y is 2. So in equation 1, we get y equals 1 plus 1. That makes 2. In equation 2, we get y equals 2 to the power of 1, which is also 2. So therefore they are both going through, are at the point 1, 2. Okay, so by substitution, I've shown these two curves are going through the point 0, 1 and 1, 2. Part B, sketch the two curves and shade the region between them. All right, the first graph, y equals x plus 1, is a straight line. Its y-intercept is 1, and it has a gradient of 1. Because I know 2 points, my 2 points were 0, 1, and the second point was 1, 2. That will just make it, if I do that first, so this point here is the 1, 2. That makes it very easy to sketch my line because it gave me those 2 points. Okay? The other graph was y equals 2 to the power of x. That's an exponential graph. Okay? The y-intercept, well, we already know. It has to go through that point and that point. The y-intercept of an exponential graph is 1. So it is going to go there. It's going to come up here and get steeper and steeper up through there. Going through that second point as well. So we are trying to find the very narrow little sliver that is between those 2 graphs. Oh, maybe I'm getting ahead of myself. I haven't read it yet. Part C. Find the area, very tiny sliver, of the shaded region corrected for significant figures. To find the area, we always do the top minus bottom graph. Okay? My x coordinates are between 0 and 1, so they're going on my integral side. The top graph was the line, so that's x plus 1. And then I want to subtract the lower curve, which was 2 to the power of x. And I'm integrating all of that with respect to x. So the dx on the end, please. Try not to forget it. I know it's easy to forget, but try to make sure you put the dx on there. Okay? Then we want to integrate. Square brackets. Integrating x, we get x squared over 2. Integrating 1, we get x. Ooh, fun times ahead. Integrating 2 to the x. Okay, go back to our formula, which said that, where is my formula? I want the log of a f dash x times by a to the power of f of x. That's on the previous page, the formula for... Oh, that was the derivative one. I want the one underneath. Sorry, I better go back. We better look at it. There it is. So the derivative was this one, but I'm integrating, which reverses that. So that one's on here for you too. Okay? So I'm integrating. As long as I have the derivative of my function in front of my a to the x, then it's going to be the a to the function over log base a. All right, do I have mine in the right form? What is the derivative of my function? I have 2 to the x. That's what I'm trying to integrate here. So x is my function. What is the derivative? This is 2 to the x here. What is the derivative of the x? 1. I just need to have a 1 in front of it. I can have a 1 in front of it. Right? So that means I can go straight over here to this form. It's going to be 2 to the x over log base 2, because a is 2. All right, so here we go back here. It's a bit annoying, it's on a different page. Oh, too far. There it is, all right. So it's going to be minus. I do have a minus sign. 2 to the x over log base 2. Log base e of 2. Between 0 and 1. All right, that was using the integral formula. Will, can you stop talking, please? Sub into the definite integral. So subbing in 1. 1 squared is 1 over 2. Plus 1 minus 2 to the power of 1 over ln of 2. Okay, that's 1 subbed in. Minus, sub in 0. 0 squared over 2 is still 0. Plus 0 minus 2 to the 0 over ln of 2. That is not 0. Okay? So you can't forget, you can't just go, oh, I'm subbing in 0, everything's going to disappear. There's something right there that I have to include. All right, so we've got half plus 1, that's 1.5, or 3 over 2, minus 2 to the 1 is just 2 over ln of 2. And then the minus and the minus will make a plus. 2 to the power of 0 is 1 over ln of 2. All right, what else can I do with that? These have got the same bases, fractions, same denominators, right? So these fractions can actually go together. I have minus 2 plus 1. What does that make? Minus 1. So it's 3 over 2 minus 1 over ln of 2. Anyway, I've probably done too much work here because the question did say, at the end of the day, I want 4 significant figures. So as long as you've got it simplified down enough, you're going to type that in. And we want 4 significant figures. The 0.0 doesn't count. Those zeros don't count. So it will be 5, 7, 3. Last number is 0. Because the 0 on the end will count. Alright, so that's 4 significant figures. Alright.